Good evening, scholars. Good evening. Please, if you can hear me, kindly comment that you can hear me so we can start, please. Can we hear me? If you can hear me, kindly comment, please. Please, if you can see the screen, can you kindly drop a comment so I can know you can? So we'll begin. All right? Can we can we hear me first of all? Can you hear me? Can you hear me? Can we hear me? If you can hear me, can you drop a comment, please? Can we hear me? All right, so please, before we start, kindly share this with your friends, share with all your UTME friends. Sorry, we are starting late. We are quite almost 30 minutes late, but it is what it is. That's Nigerian network for you. So please kindly share the link once again with your friends before we commence. We'll be starting soonest, just very soon. So please share the link before we begin. There are still a lot of people yet to be here that have been anticipating this class. So please make it known to them. All right. I believe we can all hear me, right? Are we good to go? All right, let me be sure we are good to go before we start. All right. Okay. All right, we will soon start. Please get your notes, get your writing materials. Ready? And share the link with your friends and loved ones. It rained here, so um, three concepts. Separation techniques. Please share the link. Share the link. We've taken so much time already. Right. Taking so much time already. So shall I start with separation techniques? So shall we start with separation techniques, right? Um, this is not quite good here. All right, let me do some readjustments. So let's begin. Once again, if you know any of your friends that is not here, kindly inform the person to be here right now as we begin. Now, when we talk about, um, I want you to know that this particular class is structured for revision, not to teach you everything in chemistry, because you cannot use one night to cover the whole jam syllabus, right? So basically, I might be skipping a lot of things, but I will be basically pointing out the most important things you need to know for your exam. This is more like a brush up. That's why it's called a revision, right? To brush you through the important things you need to know as regards jam chemistry. All right. All right. So please, as someone that had 90% in jam chemistry, I can assure you that safe friends, and as far as chemistry is concerned, you wouldn't have a problem if you would follow us from the beginning of this class. Right, let's get started. I hope you can, I hope my voice is a bit audible anyway, but just let's manage what we have for now. Subsequently, we'll make provisions for a better audio. Right, so when we talk about separation techniques, I'm just going to list out the most important ones you need to know for your exam, how you can identify them, like from the questions, when they ask questions, how you can easily identify them. So when we talk about separation technique, we have the separating funnel. Separating funnel. We have the um, we have fractional distillation. Fractional distillation. We have crystallization. Crystallization. You have chromatography. Chromatography. You have decantation. also have other ones like magnetization and the rest, right? Fractional crystallization and the rest. So basically, we are going to focus on these. When we talk about magnetization, it just has to do with separating magnetic substances from non-magnetic substances. So if you have ion filings in sand, you want to separate the ion filings from the sand, just use a magnet. Separate the ion filings will get like to the magnet, and then you'll be left with the sand, right? That's basically for magnetization. Now for separating funnel, this basically works on the principle of miscibility, or let's say immiscibility instead of miscibility. Let's say immi. I hope I got the spelling correctly. Immiscibility. That's for substances that are not miscible. A good example of this is when you have oil and water, petrol and water, right? So these are like, I'm giving you typical jam type of questions, right? Once you see oil and water as a mixture and you are asked to pick the suitable separation technique, then you are talking about separating funnel, right? Talking about filtration. Filtration is simply used to filter. When we use a filter paper, in filtration we use a filter paper. That filter paper is being shaped. It's just like a paper from the name, but it's being shaped like a funnel, right? And it is used to separate substances that are solid or solute. When you have something like a solution of chalk in water, for instance, and you want to separate the water from the chalk, so you just have to pour in the solution into the separating funnel. The chalk, which is solute, right? Solute is, the equation. It's important here anyway. When you have solute plus, we'll still talk about it later anyway. Solute plus solvent will give you a solution. A solute plus a solvent will give you a solution, right? So now, when you pour in the water, like I was saying, the solute, which is the chalk particles, right, will dissolve, will be left on the filter paper, while the water, which is the solvent, will pass through the filter paper. You'll now be left with the chalk particles, as the sediments, right, will be left on the filter paper, right? That's why we also have something like sedimentation, when you allow something to settle down, right? Before, that's usually used in decantation anyway. All right, now let's talk about sieving. Sieving is very common, right? Sieving is very common. It's used in Gary production. So this is a typical exam question. All right, sieving is mostly used in Gary production. That's when it's used to separate. There's a question under the sieving. You can ask something like, the question might come in this form: which of the following is used to separate large particles from smaller particles, or vice versa? Yes, you use sieving. So when you have something like I said in Gary production, you have a sieve. A sieve has what we call a mesh. All right. A sieve has what we call a mesh. The mesh is like those openings in a sieve that you use to separate smaller substances. So in a sieve, smaller substances pass through the mesh, while the larger particles remain on the sieve and are in turn separated. So you've succeeded in separating the larger particles from the smaller particles. That's when we use a sieve. Then in distillation, the difference is, I want you to note something. Distillation has to do with boiling. In distillation and filtration, in distillation and fractional distillation, boiling is involved. It has to do with you having a setup where you have what we call a condenser. Specifically, you can't hit in your exam. You make use of what we call a Liebig condenser. A Liebig condenser in your exam. Now, the difference I want you to note between distillation and fractional distillation is in distillation, the temperature range is what is wide. Distillation has to do with wide temperature range. Let me put that down. Wide temperature range. Clean this mesh. Then fractional distillation. Excuse me. Fractional distillation, you have close temperature range. So for fractional distillation, you have close temperature range. So example, you can have something like water 100 degrees Celsius and ethanol 78 degrees Celsius. Now when we talk about distillation, it's simply a means of separating two liquids, all right? It's of different boiling points. Two liquids of different boiling points. Now, what happens is that liquid, let's say you have a container that has a mixture of both water and ethanol, right? Now, what's going to happen is that you have to set up the material, maybe the container, that maybe you can pour the mixture on a beaker, for instance, and then heat it up on a Bunsen burner, right? Once that mixture begins to boil, what do you think will happen? Now, if we have a mixture of water and ethanol, which of them do you think will boil, will be collected first? Now, mind you, in distillation, what happens is that when the mixture is heated, the substance, the liquid with lower boiling point is first collected through this, all right, the condenser. It is collected as it is vaporizing. You know, when something boils, that boiling is like a means of changing something from liquid to gaseous state, right? So when it begins to boil, you see that it will start changing into the gaseous phase would emerge, right? So instead of allowing the gas to just evaporate into the atmosphere, you collect that gas through what we call a condenser, right? A Liebig condenser. It's a popular, you can see it in your exam, right? A Liebig condenser. Now, that is for ethanol. That means ethanol will come first in this case, because when you are counting 1 to 100, you count 78 before you count 100, right? The boiling point of water is 100 degrees Celsius. The boiling point of ethanol is 78 degrees Celsius. That means ethanol will be collected first before water. This is a typical example they normally use when it comes to distillation. In fractional distillation, they usually use separation of petroleum, right? Petroleum particles. Petroleum contains a lot of organic compounds. Petroleum contains a lot of organic compounds, all right? So mixtures of the components of the mixtures or the components of petroleum are separated using what? Fractional distillation, because of their close temperature range. That's their close boiling points, right? The boiling points, I think instead of this temperature range, you should have written close boiling points. Let's change that to wide boiling points. All right, that will make more sense. Wide boiling point range. That makes more sense. Wide boiling point range and close boiling point range. Now, in fractional distillation, the temperature, or their boiling points are usually close, right? So we make use of fractional distillation. It's also used in what's what we call fractional distillation of air. All right, we also use it, right, for purification of nitrogen. It's another popular example, you can see it. Nitrogen can be collected using which of the following methods? You see, A, distillation, B, separating funnel, C, blah blah blah. Just know that the answer is what? Fractional distillation, right? Now when you get to crystallization, I'm just going to hit the nail on the head, just tell you what you know, what you need to know. When you get to crystallization, just know that the keywords you should be looking out for right here are salt, sugar, sugar, drug, purity. Now, when we talk about substances that need to be pure, when we talk about the purity of a substance, we mostly make use of crystallization. So once you hear salt, salt has to be pure. Salt has to be like, it has to be on its own. If you don't have salt, like if salt contains mixtures, you know that it definitely doesn't make sense, right? So when you talk about things like this that need to be pure, that needs to be pure, devoid of impurities, right? We make use of crystallization. And the key things they usually ask is, in the preparation of drug, which of the following separation techniques is used? You see crystallization. In the preparation of salt, sugar production, make use of what? Crystallization. So don't forget. Now, when you get to chromatography, the key thing to know about chromatography, it has to do with, it works on the principle of migration actually. It works on the principle of migration. And once you hear chromatography, C for color. C for color. The C in chromatography stands for color. Right? Also, once you hear chromatography, know that we are dealing with color. So anything that has to do with color of mixtures and separating them, we make use of chromatography. Right? So, and when we say migration, what we mean is that when you have a column, right? In chromatography, we have a column, right? And we have phases. When you have different colors in different phases, right? Now, the one with what plays a role here is what we call density. The denser a substance is, more like take it as the more heavy a substance is. Density is mass over volume. That's the ratio of the mass and its volume, right? The more heavy a substance is, the lesser the tendency of that substance migrating faster. That's when we get to diffusion, Graham's law of diffusion, right? The more heavy a substance is, the lesser the tendency of the substance migrating, right? So that means the substances that will migrate first and leave the column are the less dense substances will migrate first before the more dense one. So when we talk about chromatography, what you should be looking out for is anything that has to do with color. So when you hear a question like, which of the following is used to separate a mixture of dyes? Paints, etc. So when we talk about paint has to do with color. We have different colors of paints, white, red, blue, whatever. Dyes too has to do with colors, right? So now once you hear anything that has to do with color, just know that the answer is chromatography. Like, don't waste your time. It's one of the easiest questions you find. Once you look at the question, you're talking about separation technique, and you are seeing something that has to do with color in the question, just look for chromatography. It has to be in the option, and pick it and move to the next question, right? Then decantation is what most of you guys used to drink garri, right? When you are pouring out the upper layer, that's the upper layer of a particular maybe mixture, right? So that you'll be left with the lower layer, right? So pouring out the upper layer and so you'll be left with the lower layer is what we call decantation, right? And that's basically a summary of what you need to know about separation techniques. Let's dive into next concept we need to talk about is the concept of boiling and melting point. Now, note that boiling point, melting point. Now, boiling point is the temperature at which a liquid turns into a gas, right? So, liquid to gas. This is solid to solid to liquid, right? That's the difference between boiling and melting point, right? Now, like that is a temperature, a specific temperature, and I want you to know that the temperature during change of states, like this is what we call vaporization. This is melting. So we are still going to talk about other change of states, but I want you to know that during change of state, temperature is constant, right? Temperature is constant. So temperature is always constant during change of state, right? Once a substance is transitioning from one state to another, then the temperature will always be constant, right? Now, there's an important question they used to ask about impurities in boiling and melting point, right? Impurities. When you add impurities to so now, when you add impurities to a substance, what happens to the boiling point? Does it increase or decrease? Right? Now, it is important to know that impurities increases impurities increase the boiling point of a substance, of a liquid, right? So for a liquid, the boiling point will increase, right, if impurities are added. While for a solid, the melting point will decrease. Or you will see reduced. Okay, let's just remove the D's anyway. So when you add impurities to a substance, or a solid substance, the melting point will reduce. That means if the melting point is supposed to be, let's say, 50 degrees Celsius, that means if the temperature needed for that solid substance to melt is 50 degrees Celsius, adding impurities to it will make it melt faster because it will reduce that temperature to something like 30. And you know 30 is closer than 50. That means when you have reduced the melting point by adding impurities, that substance will melt faster. Now, a good application of this addition of impurities is when you have snow or ice falls. Or let's just leave it with snow anyway. Now there's a question in JAM past question that has to do with ice on the road, right? Right. When you have ice on the road and then you want that ice to melt fast, what do? You sprinkle salt. That's a JAM question. That salt was sprinkled. Salt was sprinkled. Salt was sprinkled on the road surfaces so as to reduce the melting point of that ice, so that the ice will quickly melt and to avoid dot. You understand? So that is application of boiling and melting point. Right. Now let's talk about change of states that you need to know. All right. Change of states. I hope you are still with me. Kindly inform your friends that are not here to be here, please. Right. Now, let's move. For change of states, we have basically, there are three states of matter, right? We have the solid, liquid, and gas. Now we are going to take it in each direction. We are going to take solid to liquid, solid to gas. No, let's take it this way. Solid to liquid, liquid to gas, solid to gas. Then we do gas to liquid, gas to solid, then liquid to solid. Alright, so let's take that. Now when a substance is changing from a solid state to a liquid state, it is doing what? It is melting. So that change of state from solid to liquid state is known as what? Melting. From liquid to gas, when a substance changes from liquid to gaseous state, it is vaporizing. So you can have different forms. This is evaporation, vaporization, you can also have boiling. So any of these options is actually accepted. Evaporization from liquid to gas, vaporization from liquid to gas, boiling from liquid to gas. Now from gas to solid, what do you have? Sublimation, right? Sublimation. Now, in sublimation, they usually have examples, right? Examples are they usually asked. Good examples are ammonium chloride, that's ammonium chloride, that camphor, right? You have iodine. These are examples of substances that can sublime, right? There might be other examples unless solid ice, dry ice. Dry ice is solid carbon dioxide. So dry ice is solid carbon dioxide. These are examples of substances that can sublime, undergo sublimation, change from solid to gas. Alright. So in case you are lost, this is solid to liquid to gas. Alright, so you know what the symbols entail. Now from gas to liquid, what is happening? Gas to liquid, it is what? Condensing. Right. From gas to solid. Notice something. Gas to liquid is opposite of liquid to gas. So opposite of evaporation is what? Condensation. Opposite of sublimation is what? Deposition. Deposition or desublimation. Deposition or desublimation. From liquid to solid, that's opposite of solid to liquid. What are you going to have? I'm going to have freezing. Example, freezing of water. So let me clean that. You have freezing. Or you can have it as solidification. any of them is acceptable. All right. So basically, that's it's about um, the separation techniques and melting and what have you. Now we're going to move into chemical. Before we talk about chemical combination, I'm going to move into a very important aspect that we need to know. Some people don't know how to. I'm really sorry. I'm going to be moving really fast. All right. So if you are jotting down something, you have to jot that down really fast. All right. So now let's proceed. Now let's use this. So this 1, 2, 3, 4, 5, 6, 7, 8. Alright. For your level, just see it as that. Just know that these first 20 elements they are in groups 1, 2, 3, 4, 5, 6, 7, 8. From this, I'll touch periodic table, touch periodicity, and I'll touch chemical combination with this, and I also touch how to get the formula of organic compounds. Right. Now, that's what we call duplet and octet structure. Right. Duplet. From duplex, you have to octet. You have 8. Now, all these elements would always want to attain the octet structure, except 1, 2, 3, 4, 5. So, except the first 5. Except the first 5, the rest will always want to attain an octet structure. Now, I'll show you why the first 5 will attain the duplet structure. Now, the essence of attaining either duplet or octet structure is what? For stability. Right? For stability. For stability. Right? Now, when we talk about stability of organic compounds, stability of elements, right? Let's start with hydrogen. Now, hydrogen is not a group 1 element. If they ask you, tell them that I said that hydrogen is not a group 1 element. Now, I'm going to show you why. In advanced chemistry, hydrogen can comfortably be placed in 3 groups. 3 different groups. Hydrogen can be placed in group 1, hydrogen can be placed in group 4, and hydrogen can be placed in group 7. I'm going to show you why. The reason, because of this particular fact, that's why in advanced periodic table, in a standard periodic table, you see that you notice that hydrogen is usually placed at the center, somewhere here. If you have seen a standard periodic table, you see hydrogen somewhere at the center. That is because hydrogen doesn't completely fit into the group 1 element and completely fits into any other group. Right? Now there's what we call anions, cations, positively charged, negatively charged. When elements in chemistry, this is different from what you know in your daily life. In daily life, plus means addition, right? Plus means gaining. When you gain something, that's a plus. When you lose something, that's a minus, right? But in chemistry, in periodic table specifically, when we are talking about periodic table, it is the opposite. What did I say? It is the opposite. minus, listen now, before some of you used to misplace it. When these are what we call ions generally. Or let's keep it like this, keep it simple. This is, how do I change this now? Ions. So the two of these are altogether known as ions. Notice that they both ended with ions, anions, cations. Right? These are elements that have a charge on them. That is, elements that have either lost or gained an electron. The reason why elements attain charges is because they've either lost or gained electron, and their loss or gain of electron is dependent on this. It's actually for stability. It is actually for the sake of stability. They want to be stable. By being stable, I mean they want to attain either duplet structure or the octet structure. So by so doing, they will either lose or gain electrons to attain stability, hence having a negative or positive charge. So what does that mean? Like I said, in periodic table, it is the opposite. That means a negative charge, does it mean loss or gain of electron? Negative in the actual sense means loss. Negative means minus means loss. But in chemistry, negative means gain. So when you have a charge, when you have an ion that has a negative charge, it means that that ion gained electron. Don't misplace, don't forget it in your life. When you have an ion that has a negative charge, it means that that ion did what? Gained electron. When you have an ion with a positive charge, it means that that ion did what? Lost electron. That ion did what? Lost electron. Now, let's move. Like I said, they either tend to attain octet or duplet structure depending on what you have. Now look at hydrogen. Hydrogen is the first element in the periodic table. That means what's the electronic configuration? Electronic configuration of hydrogen, in the first shell to have only one electron, right? To have only one electron in the first shell. Now, the only way for hydrogen to be stable is to do what? To attain, to gain one more electron so that it will have a duplet structure, right? So when hydrogen gains one more electron, to have a duplet structure. And what happens when an element gains electron? It attains a negative charge. But hydrogen said no. Hydrogen is the only element that the ionic form is like this, H plus. Meanwhile, other elements will gain electron and have a negative sign, but hydrogen will gain electron and have a positive sign. That's the number one reason why hydrogen tire even chemistry, even Lavoisier. The thing just tire everybody. They don't see better group to keep and they just put them for center because the guy know they gree. The guy know they gree. Others used to have negative sign when they gain electron. You reach your term, you say a positive sign, you won't get. That's number one default hydrogen has. Now let's continue. We'll still get back to hydrogen later. Let's look at helium. This helium. Helium is the second element. After hydrogen, you have helium. So helium is the second element in the periodic table. That means that helium will have what? 2 electrons. Because it is the second element, it's going to have 2 electrons. Second element, 2 electrons. So now, what does that tell you? 2 electrons is already duplet. So does helium need to lose or gain anything? No. The answer is no. Helium does not need to lose or gain anything because it is already duplet on its own. It is already stable. And that is why you hardly see elements that contain helium. I mean, you hardly see compounds of helium, right? Because helium is already stable, so it is very weak. It is very less reactive. It is less reactive. It is less reactive. In fact, group A elements are the least reactive elements in the periodic table because they are already stable. The essence of elements combined together to form compounds is actually because of stability. It makes them more stable. But because these guys are already stable, they hardly react with other elements in the periodic table. Is that okay? Now, let's move to lithium. Lithium, give you 1, 2, 3. Are you with me? Lithium is the third element in the periodic table. So it's going to have 3 electrons. That is 1, 2, 3. Note that the first shell will always have 2 electrons. The first shell cannot have more than 2 electrons, but it can have less than, as in the case of hydrogen when it was 1. But once it passes 2, you create another shell. The second shell will have what? 8. Alright? But when you advance, in fact, it's important to know that there's a formula for calculating the maximum number of electrons in a shell. I'm going to give you that. I'm also going to give you that of orbitals too. You need them. Right? Just calm down. Right? We're going to, periodic table is the bedrock of chemistry. If you understand periodic table very well, chemistry is going to be very sweet for you. Right? Now, let's proceed. So because lithium has 1 electron in this atom shell, there are 2 possible things that can happen here for lithium to be stable. That is, either it attains duplet or octet structure. Now, let's look at it. For lithium to attain duplet structure, how many electrons does it have to lose? 1. It just has to lose this particular electron. If it loses electron, what will happen? It will go back to this. You'll be left with this. If this electron is lost, that means this entire shell is lost. If that electron is lost, that means the entire shell is lost. And if the entire shell is lost, we are left with 2 electrons. And what does this tell you? It tells you that, okay, now let's look at the second scenario. That is for to attain duplet structure. Now what about attaining octet structure? Let's draw it again. What about attaining octet structure? For this to attain octet structure, now I want you to know that, I want you to know that octet and duplet structure means that the maximum number of electrons in the atom shell is 2, and the maximum number of electrons in the atom shell, that's what duplet and octet structure means. So when you say something has octet structure, it means that the maximum number of electrons in the atom shell is 8. When you say something has duplet structure, it means the maximum number of electrons in the atom shell is 2. Now, for lithium to attain octet structure, it means that it has to gain extra 7 electrons, so that you add it to this one to make it 8 in the atom shell. But look at it, it is easier to lose this one to go back to duplet than to gain extra 7 to attain octet structure. So lithium looked at it. What's the point of stressing myself? What's the point of wasting energy to get extra 7 electrons when this one out and then attain my duplet structure and still be stable? So what did lithium do? Lithium was like, there's no point stressing myself. Since I can just lose this and attain stability, I'll just lose that. And when I lose 1 electron, what happens? Let me write it so you guys will flow with me very well. Loss of electron. This anion is gain. Cation is loss. Alright. So when I lose electron, I have a plus charge. So lithium will have a +1 charge. +1 charge because it lost only 1 electron. If it's 2, it will be what? +2. But we don't just write the 1, just like we don't write 1x, but we just say x, because we already know that x is 1. So there's no point writing 1 in front of it. We already know that the plus is 1. There's no point writing 1 to the plus again. Do you understand? Good. Now, flow me. Beryllium. This is beryllium. 1, 2, 3, 4. Beryllium is the 4th element, so it has 4 electrons, 2 in the first shell, 2 in the second shell. Now let's look at it again. For it to attain duplet structure, it has to lose these 2 to go back to duplet structure. For it to attain octet structure, it has to gain extra. Now look at it. It is easier to lose 2 than to gain extra 6. So what will beryllium do? Beryllium will not stress itself. Beryllium will just choose to lose these two and go back to duplet structure. I see it. Beryllium will lose 2 electrons to go back to structure. And when it loses 2 electrons, it will have what? A +2 charge. But we write it as 2 plus in chemistry. We don't write it as +2, we write it as 2 plus. Remember, I told you loss of electron means plus. Loss of electron means addition sign. Gain of electron means what? Negative sign. This marker that has been falling when you're not London Bridge. Now, let's continue. Let's move to boron. For boron, you have 1, 2, 3, 4, 5. This is boron. The first shell has 2, the second shell has 3. Now, the same thing will happen. It will lose the 3 to go back to the plate because it is easier to lose 3 than to gain extra 5. The energy needed to gain extra 5 is much higher than the energy needed to lose 2. So what will boron do? Boron will just not stress itself to just do what? Attain no stress. Notice the difference between beryllium and boron. Beryllium is Be, boron is what? B. Right? Clear? Clear. Let's continue. Now, onto carbon. Carbon. No, carbon is a very popular element. Right? I think one of the most popular elements we have in periodic table is carbon. That is after you have oxygen and hydrogen. Hydrogen and oxygen are very popular. Then you have carbon. You agree with me that carbon is a very popular element, and there are reasons why it's popular. Now let's get to carbon. Okay, let's use this ink. Carbon. Okay, let me draw this smaller. Carbon. 1, 2, 1, 2, 1, 2, 3, 4. Now look at it. As carbon is the 6th element in the periodic table. 6th element in the periodic table. That means carbon will have what? 1, 2, 3, 4, 5, 6 electrons. 2 in the first shell and then 4 in the outermost shell. Now this is where it gets interesting. It has 4 electrons in the outermost shell. So what will happen? If it loses 4, it will gain duplet structure. If it gains 4, it will gain octet structure. There are equal energies needed to gain either duplet or octet structure. So if it will take you the same energy to lose something and the same energy to gain it, will you prefer to lose or to gain? You prefer to gain, right? Simple logic. That is why carbon would prefer to gain. Carbon will prefer to what? Gain extra 4. Remember, gain of electron is what? Negative sign. That's why you have this negative sign. So when carbon gains extra 4 electrons, it attains stability. Right? It attains octet structure. That is for carbon. Now let's move to nitrogen. Nitrogen. You have 1, 2, 3, 4, 5, 6, 7. This is nitrogen. It has 5 electrons in its outermost shell. How many is left to attain octet structure? Just 3. So it's easier to gain 3 to attain octet than to lose the entire 5. Are you seeing it now? 3 is closer than 5. So it's easier to lose 3 than to gain 5. So my guy, we decide to gain 2. We decide to gain 3 more. And when it gains 3 more, it will attain what charge? What charge will it attain? Tell me. I don't know. Tell me. Nitrogen will attain how many charge? This is the ionic form of nitrogen. minus 3 because it's gained 3 electrons to attain stability. So if you do the same thing for others, you get the same thing. Oxygen has what? 6 electrons in its atom shell. It will lose 2. It will gain 2 to attain what? Minus 2 charge. Fluorine has 7 electrons in its atom shell. It will gain 1 to attain what? Minus 1 charge. Neon has 8 electrons in its atom shell, so it's not going to gain, it's not going to lose because it is already stable. Remember what I told you, all group 8 elements are stable, hence they are the least reactive elements. Take note of that. Right, so we've established that the charges on these are +1, +2, +3, or you can write it in the chemistry form. So that some people will say, so I thought you said you don't used to write the number before. Let me do that for you so that you not beat me. So you know beats me. 3 minus 2 minus 1. So this is 1 minus and then this is 0. That's why sometimes they are also called group 0. That's group 0 elements because they don't have any charge. They are chargeless. Alright. Alright. So now let's move on. Let's move on to the main reason why. Draw this thing, note this thing. This thing I explained to you. If you know this thing and know it very well, chemistry will be flowing easily for you because this is the bedrock of chemistry. Understanding periodic table very well, the in-depth of periodic table is going to make it easy for you to understand chemistry. It's going to make it easy for you to understand chemistry. Likewise, when it comes to physics, now you know measurements, units, dimension. Those are the bedrock of chemistry that will make you understand physics very well. When it comes to English, you have it too. You have the word class, right? Biology, you have classification and cell. These are things that will make you understand the concept very well, right? And let's proceed. I'm going to use this to show you how to form the chemical formula of some compounds. But before that, let me give you some common radicals that you need to know. Common radicals. No? Common radicals. So I'm going to give you some common radicals that you need to know. Number 1, you have nitrates. NO3 minus carbonate. CO2. This is 3. So you see it's very. I'm going to give you time to write. Then we move. Alright. Sulfate. I'm just going to give you the commonest ones. I might not give you everything. Just the commonest ones. Right? Manganese. Which other common one? Sulfide. Phosphates. Right, so that's 3 minus, then that's 3, 4, so 5. Okay. Which other one? Okay, hydroxide. 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 Okay. Should I give you? Okay, let me just give you the last one. Though it's not that popular one. Let me give you chromates. Right? So these are the 7 common radicals in stride. Write them down and I'll tell you why you need them. You need them very, very importantly. Right? So get them down as you proceed. So, sorry, in case you can't see them very well, this has a 2 minus charge and then a 4 below it. This has a minus 1 charge and a 4 below it. 3 here, 2 minus, 3 minus, 4 minus, minus, 4, 3 minus, 3, 2 minus. Right? So now, if you know these radicals very well, and their charges, this is trioxonitrates 5. I'm going to tell you how the numbers came about. Just follow me. This is oxygen. And when oxygen combines with elements, most times, in fact, it's only the group 1, group 2, and group 3 that doesn't change. How do I mean? Now, it's only the group 1, group 2, and group 3. They are metals, right? These are metals, apart from hydrogen, which I've said earlier. Oh, I forgot to explain to you how hydrogen can comfortably be placed in 3 groups. Now, let me explain to you. Before you say this guy just talked, later I explain. Let me explain to you why hydrogen can be placed in 3 different groups. Number 1, hydrogen can be placed in group 1 because group 1 elements have 1 electron in their outermost shell. If you check, do the electronic configuration of lithium, what are you going to have? Okay, let's do it. Hydrogen. Hydrogen has just 1, right? Hydrogen. Lithium. Sodium. Sodium will give you. Sodium will give you. Sodium will give you 1, right? Then, if you do for potassium, you have to add another shell too, right? So what does that tell you? It tells you that group 1 elements have 1 electron in the outermost shell. So we can choose to place hydrogen in group 1 with the mindset that hydrogen has 1 electron in the outermost shell. So since every element in group 1 has 1 electron in the outermost shell, then we can place it in group 1. Clear? Clear. Good. Now, let's look at group 4. hydrogen can be placed in group 4 because group 4 elements are half filled. What did I say? I believe you've written this down. I can clean it now. Okay, let me just wipe this. Group 4 elements are half filled. Group 4 elements are half filled. What does that mean? It means that, remember when I talked about carbon, I said that carbon is the sixth element. So the first shell will have 2, the second shell will have 1, 2, 3, 4. Yeah, 3, 4. So the first shell will have 2, the second shell will have 4. What does that tell you? It tells you that carbon is half filled because it needs 4 more electrons to become stable. And it has 4 electrons already, so it needs half of half of what is needed, it already possesses. So it just needs the same thing that is at the outermost shell. So it is half filled. The outermost shell needs 8 electrons to be stable, right? But it already has 4, which is half of 8. Now let's look at hydrogen. Hydrogen has 1 electron in its outermost shell. It needs 1 more to become stable, to attain duplet structure. I mentioned duplet structure. Duplet structure has what? How many electrons in its outermost shell? 2. How many electrons does hydrogen have normally? 1. What is half of 2? 1. That means hydrogen is half filled, and group 4 elements are half filled. So hydrogen can be placed in group 4 with the mindset that it is half filled. This thing I'm teaching you now, you will not see it in your O-level textbooks. This is chemistry. In fact, even the 100 level self, most times you will not see it. The only reason I know this is that I kind of read a textbook of a chemistry graduate, right? Some people that have done it in 300 level, 400 level. Complex is called inorganic chemistry. It's an advanced book. Textbook is quite large. So this you will not see it in your O-level test, but I'm just giving you for free, right? Now, next is group 7. Group 7. Now, I don't want to draw everything, but we've already established that group 7 elements have 7 electrons in their outermost shell. So now how you know the group an element belongs to is simple. It's just the number of electrons in this outermost shell to tell you the group. If the element has 6 electrons in its outermost shell, not the total number of electrons, I mean in the outermost shell. If the outermost shell contains 6, then it is in group 6. If the outermost shell contains 5, then it is in group 5. If the outermost shell contains 7, then it is in group 7. Now, back to what we are talking about. Hydrogen can be placed in group 7. Why? What does group 7 elements need to become stable? Who can tell me? Group 7 elements they just need 1 more electron to become stable. Let's draw hydrogen again. What does hydrogen need to become stable? Simple. Hydrogen needs 1 more electron to become stable. Group 7 elements need 1 more electron to become stable. What happens? Hydrogen can be placed in group 1, group 7 because of that reason. You see? Because in the actual sense, if you say you are placing hydrogen in group 1, it is not a group 1 element. All group 1 elements are metals. Hydrogen is not a metal. Hydrogen is a non-metal. So if you have to look at it, this is even a better place to even place it here or here. Because these are non-metals. So hydrogen as a non-metal is even better you place it this side. But that's why in a standard periodic table, like I mentioned earlier, go and check online. After this session, check online. You see that standard periodic tables, they place hydrogen at the center. Check, you definitely see a periodic table online that has hydrogen at the center. check, you see one. I'm sure you see one. That is because of the inconsistency of hydrogen. Do you understand? So now that's it about hydrogen. So let's continue with our radicals. So shall we? We shall. Good. Now, having established that all these elements, these are their charges. Whenever you see oxygen combined in this combined state, just know that the charge is -2. When you see fluorine in this combined state, the charge is -1. When you see lithium, +1. When you see, just like that. Alright? Good, 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 good. Now, look at this. The oxidation number of nitrogen here. I'm going to use this thing to teach you oxidation numbers. Right? They can give you a compound, ask you to find the oxidation number of so and so in the compound. I'll use this medium to teach you oxidation number. Don't worry, you'll be fine. Chemistry is easy. You see how everything is linking. Chemistry is very. Even me that got 97, they pay me. I wanted to get 98, but you get it. Don't worry, just relax. Now, let's talk about this. This is. Now, for ions or radicals, radicals are just combination of two or more elements that have a charge. That's the difference between an ion and a radical. This is an ion. Iodide ion. This is a radical. Nitrate. Right? Why is it a radical? Because it's a combination of two or more elements. This is just an element, so you just call it an ion. Are you with me? Good. So now, whenever you have ions and you're asked to find oxidation number, calculate, sum up each of the constituent charges, multiply by the number of molecules, and equate it to the charge. I don't speak big grammar now. This is what I mean. We are asked to find, normally oxides, in oxides, oxidation number of oxygen will always be -2. So there's nothing to find. What varies is this one. These ones can vary. If you check your new school chemistry, you notice that in nitrogen and its compound, you will see that there's a place where we have nitrogen and we have different oxidation numbers nitrogen can have depending on the compound it is present in. We have nitrogen 2, that means the oxidation number of nitrogen there is 2. Nitrogen 1, the oxidation number of nitrogen there is 1. Here, triosonitrate 5, the oxidation number of nitrogen here is 5. I've seen it. So nitrogen can have variable oxidation states. Same with phosphorus, right? So all of these elements can have variable oxidation states. That's what we call them. They can exist in multiple oxidation states. So because you know that, you can't be so sure. You can't say that the oxidation of nitrogen here is -3. You have to work it out. You have to work it out. But you know that this one is always static, -2. Oxygen is -2. So how do you do it? Let's take N to be X, or you can still leave it as N. Right, since that's the one we are looking for. Alright. Since that's what we are looking for, you have it as N plus oxygen is -2. Oxygen is what? -2. Oxygen is -2 charge. The charge on oxygen is always -2. So, and there are 3 oxygen molecules there. So you just like saying -2, -2, -2 into 3 places. That's what -2 times 3, right? So we are adding, summing all the oxidation numbers, and we equate it to the charge. What's the charge? The charge here is -1. So that's the charge you are seeing here. We equate. But if it doesn't have charge, you equate it to 0. Because anything that doesn't have charge, it means that it has 0 charge. 0 is equal to nothing, right? So it does not have charge. The charge is 0, so we equate it to 0. So if it does not have charge, let's say this is what we have, then we'll now say this is equal to 0. But because it has a charge, we equate it to the charge. Now we are trying to get the oxidation number of nitrogen here, right? So that will give you N 3 times sorry, minus 2 times 3 is minus 6. So n minus 6 is equal to minus 1, right? So n is equal to minus 1 plus 6, which is equal to 5, which is equal to, let me write it very as plus 5 plus 5. So minus 2 times 3 is minus 6. Plus minus is minus. So this is n plus minus 6, which is n minus 6. Plus minus will give you minus. So anytime you have plus minus, it will give you what? Minus. So n plus minus 6. Minus 2 times minus 3 is minus 6. Just like saying 2 times 3 is 6. Add the minus sign. That's minus 6. N minus 6 is equal to minus 1. Now, we are trying to make n in spherical form. We're looking for n. We are not looking for n minus 6. We are looking for n. So when you make n in spherical form, we are going to have n is equal to minus 1 plus 6. This 6 minus 6 will cross the equal sign. Move to the other side. You have plus 6. Minus 1 plus 6 is the same thing as saying 6 minus 1. 6 minus 1 is what? 5, which is plus 5. That means the original number of nitrogen here is 5. That is why the name of this radical is what? Trioxonitrate 5. Trioxonitrate 5. Trioxonitrate 5. This 5 is for nitrogen. It's telling you the oxidation number of nitrogen there. Alright. So when we are naming some of these compounds in their combined state, their name changes. Alright, I told you that it's only lithium that will remain lithium in the compound. Beryllium will remain beryllium. Sodium will remain sodium. Potassium will remain potassium. Magnesium will remain magnesium. All these group 1, group 2, and group 3. Except hydrogen. Hydrogen is not a group 1 element. I've said that many times. Alright, so what do I mean? Notice that their name changes. Instead of oxygen, you call it trioxo. So the name changes from oxygen to oxo. Sometimes it's changed to oxide if it's an oxide. But here it's a radical, so it's not an oxide. Alright, so we have oxo. Alright, trioxo. Nitrogen changes to nitrate. Sulfur will change to sulfate in PO4. Notice that AT always has PO4 for sulfur and phosphorus. Right, so sulfate in SO4 2 minus, manganate in MnO4 minus, nitrates in NO3 minus, not NO4. Not say that most of them has 4. Notice that most of them has 4, but there are some that have 3. This one, so know them. This is sulfite. The one with 3, SO3 2 minus is sulfite. SO4 2 minus is sulfate. CO3 2 minus carbonate. This nitrates. But if you want to be specific, try also nitrates 5. This is nitrates, but if they ask you what is the oxidation number of nitrogen in the nitrates, or what kind of nitrates, you now say trioxonitrate 5, telling you that 5 is the oxidation number of nitrogen. Do you understand? So if you do the same thing, you are going to have 4 for carbon. So let's do the math quickly. This is minus 2. Minus 2 times 3 is minus 6. Carbon, we don't know what carbon is. Carbon minus 6 is equal to minus 2. So carbon is equal to minus 2 plus 6, which is 6 minus 2, which is 4. So we are going to have that carbon is equal to what? Plus 4. The oxidation of carbon is plus 4. That is why the name of this radical is what? Trioxocarbonate 4. Trioxocarbonate 4. Alright. So let's proceed. Now, if you are asked to get the correct structure of, the correct formula of calcium trioxonitrate 5, how are you going to do it? First of all, you're going to ask yourself, what are the constituents of this compound? What makes up calcium trioxonitrate 5? Alright, but before we do that, let's start from the basics. We're going to look at how to get the following structures. 1. Sodium chloride. 2. Magnesium chloride. 3. Sodium hydroxide or magnesium. So let's work with these 4 and then you can try the rest at your convenience. Now, for sodium chloride, the first question you are going to ask yourself is, what makes up sodium chloride? What are the constituents of sodium chloride? Sodium chloride is made up of sodium and chlorine. Right? Sodium and chlorine, because they mentioned sodium chloride, just that chlorine changed to chloride. I told you their names changed, except for group 1. As you can see, sodium is sodium, magnesium is magnesium, calcium is calcium. Their names don't change. It is these ones that change. Do you get? Right. Sodium is in group 1. That means the charge on sodium is what? +1. The charge on chlorine is what? -1. Sodium +1. Sodium is in group 1. The charge is +1. Chlorine -1. Chlorine is in group 7. The charge is -1. I'm showing that. So now when you are dealing with, when you have to find the correct formula, you don't do what? You don't consider the charges. You don't consider the charges. Whoa. Nigerian, if I don't do this one. Alright. Sorry. Continue. Alright. So now, I hope you can see this very well. I'm coming. This is Nigeria, where you don't have stable electricity, but we have regardless. Alright, so now let's continue. So sodium, I was trying to cover this. I was trying to say that the signs are not needed, right? The signs are not needed. What you just basically need is the magnitude as the numbers. So when you are trying to find the correct formula, what you do is you do what we call exchange of radicals. Exchange of radicals. Sodium will go to 1, chlorine will go to 1. But when you are writing them, when you are writing the formulas, the metals will always come first. Take note that Dr. Sagacious said that metals will always come first before the non-metals. So I'm going to write sodium first. Then Na times 1 is what? Na. Cl will come second. Cl times 1 is Cl. Hence, this is the formula for sodium chloride. That's simple, right? Very simple. Now let's do for the second one. For the second one, you have magnesium chloride. So you have magnesium. Let's use this method, +2. Chlorine -1. Let's use this method. So magnesium to chlorine, the same thing will happen. You cross multiply. Which one will come first? Magnesium, because it is a metal. All elements in 1, 2, and 3, they are usually metals, right? So magnesium will come first. Magnesium times 1 will give you what? Magnesium. Cl second. Cl times 2 will give you what? Cl2. And this is the formula for magnesium chloride, right? Magnesium is +2 from here, it is in group 2. So the charge will be what? +2, because it will have 2 electrons in its atom shell, and it will decide to lose 2 to attain stability, right? Good. Now on to the next. I hope you are taking notes. This is, especially, I know this thing now might be boring some people, but this is the foundation of chemistry. For the sake of people that don't know, let's treat 2 more examples and we move. I don't know when this class is going to end. Whenever I feel like maybe hope that all things being equal. We have magnesium and we have hydroxide. Now in this case, we have magnesium and we have hydroxide, and I've given you hydroxide, and the charge on hydroxide ion is what? -1. The charge on magnesium is what? +2. So let's go. Elements in 1, 2, and 3 will always come first. That's the metals. So metal will come first. The magnesium will come first. Magnesium times 1 will give you magnesium. Hydroxide times 2 will give you OH2. But are you going to leave these 2 like this? No, you cannot. I know that this 2 is for OH, not for H. If you leave it like this, it means that someone seeing it like this will think that this 2 is only for H, not knowing that this 2 is for both O and H. So what's the best way to do? You cannot say because the 2 is for both O and H, you now go and put another 2 here, so that you show that the 2 is for both O and H. No, that's not how to do it. You use brackets. So once you have number covering 2 or more elements like that in a compound, so to show that that number is for both the elements, you use what? Brackets. So we put a bracket here and we put a bracket here, and we say that this is how to write magnesium hydroxide. Mg brackets OH close brackets 2. This is magnesium hydroxide. Hope that's clear. Good. Let's do the last one. Have you taken that? Take it down and let's do the last one. There are other examples, but for want of time, let's just do this. We have calcium triazole-95, we have calcium, and then we have nitrate. So, as usual, we cross and multiply. So when you cross and multiply, Ca times 1 will give you Ca. Calcium will always come first because it's a metal. NO times 2 will give you NO. NO3, sorry, times 2. But you cannot add the 2 like this. If you add the 2 like this, it will look like it's NO32. So what do? You use brackets. That's what I said earlier. Because there are 2 elements here, so you use bracket. Sharp. So this is calcium trioxonitrate 5. Regardless of how it is, the oxidation number of nitrogen there will always be what? 5. Is that okay? Good. So this is basically the idea behind getting the correct formula of compounds. All right. So let's move. Now, before I clean this periodic table, let me just say a few things and I'll clean it. Group 1 elements are known as what? 1, alkaline metals. Group 2 elements, alkaline earth metals. Group 3 elements. Now this group 3, group 4, group 5, they have names. Like group 5 now, they have pnictogens, the icasogens, icinogens, pnictogens, chalcogens, and rest. They are not going to ask you those things. They will not ask you. You see in JAM, they will not ask you. So when during post-UTME, when we are doing our post-UTME classes, that's when they might ask you from crazy institutions like UI, OAU, Lilibel, they might decide to ask. But JAM, that's advanced. It's not your O-level textbook, so they will not ask. Only what is in your O-level textbook will be asked. So if you are looking for group 3 elements, group 3 elements, you can call them the boron family. The first element there, use it for the family, the boron family. Group 4 elements, the carbon family. Group 5 elements, the nitrogen family. Though they have names just like these ones, but they will not ask you because they are advanced for your level. Group 6 elements, you call them the oxygen family. They will not ask you group 7, but the one they can ask you is what group 7. You know that one already. Halogens. They will ask you group 7 and they will ask you group 8. So only these 4, these are the only 4 they will ask you. They cannot ask you other ones. So they have their names. During post-UTME, we tell you that chalcogens, pnictogens, icosagens, and so on and so forth. Anyway, but we prefer to call this carbon family, right? Then group 8, we have the inert gases or noble gases or rare gases. So they are called the inert, noble, or rare gases. Right? The gases are rare in nature. They hardly combine, right, with elements. So these are the basic ones you need to know. Right? Now, group 1 to 3 are basically metals, and then 4 to 8 are non-metals. And this is for the first 20 elements anyway. For the first 20 elements. Alright, so take this down. If you are done, then we move. Alright. I believe I can wipe that off now. Thank you. Now, another question they can ask in periodic table is the most electronegative element. The most electronegative element is fluorine. Fluorine is the most electronegative element. You see, they look alike. The most electronegative element, fluorine. The most electropositive element, francium. Francium is written as fluorine is written as so fluorine is the most electronegative element. Francium is the most electropositive element. Francium is the last element in group 1. Francium. Down in group 1. Fluorine is the first element in group 7. Technically, this first element would have been the most electronegative if it was reactive. But it was not reactive, that's why we shifted it to this. This is my man here, fluorine. because electronegativity and electropositivity are opposites to opposite things. So I'm going to give you the trends now. You need to know. I'm no long story. I would have explained everything for you how they came about, but there's no time. There's no time. We are we are we are running ahead. We're trying to know who can cover. We might not finish everything like I said in the work. As much as we can cover before our light goes off, because this is Nigeria, we'll do that. So now, atomic radius. Atomic radius. Electronegativity. Electropositivity, sorry. Slash metallic character. Metallic character. Alright. Okay, let's leave this to ionic radius. Size. So I would have loved to explain these things in their fullness, but for want of time, it won't be possible. So let's just leave it there. So these are what we call periodicity of elements, periodic trends of some properties in periodic table. So these three properties I wrote now, they do what? Decrease across the period. And increase down the group. This is on a general base. So these three properties, they decrease across. That means across this is across the period. That is, as you move from left to right in the period, this is your left. If you stay this is my left, this is my right. So as you move from left to right in the periodic table, atomic radius decrease. That is generally, on a general basis, atomic radius will decrease. That means atomic size, the size of this will be smaller than the size of this. So right, the size of this will be smaller than the size of this, because it is reducing as you are going to this. That means the size of this will be smaller than this. That means the size of this is supposed to be bigger than the size of this, because it is reducing as you go. So maybe if you have bigger size, as you go here it will become smaller, as you go here it will become smaller, as you go here it will become smaller, just like that. Do you understand? Same with electropositivity or metallic character. Of course, it's obvious, electropositivity decreases. As you move from left to right, you move from metals to non-metals. That is, you move from positivity to negativity. So positivity increases this side, but it reduces this side, as you can see. So that's why as you move from left to right, electropositivity or metallic character decreases. But as you go down, it increases. That is why down the group here, francium has the highest metallic character. That's why francium is most electropositive. Alright, ionic size too is just like the size of an ion. Atomic size is the size of an atom. Right? That is for these ones. Now I'm going to give you another three that will do the opposite of this. That is another three that will increase across the period and decrease down the group. These ones will decrease across the period and increase down the group. Decrease across the period, increase as you go down each group. So as you go down each group, number of shells keep increasing. Take note of it. As you go down a group, the number of shells do what? Increase. Number of shells in period 1. The number of shells also tells you the period an element belongs to. Take note of that. So if you do the electronic configuration of all this, notice that hydrogen has one shell, telling you that it is in period 1. Lithium has 2 shells, telling you that this is the first period. Period 1 has only hydrogen and helium. Period 2 has lithium, beryllium, boron, and the rest. Period 3 has sodium, magnesium, and the rest. Period 4 has potassium, calcium, and the rest. So in period 1, the number of shells present is just 1. That is why they belong to period 1. Period 2, the number of shells present is 2. That is why they belong to period 2. Number of shells present for this is 3. That is why they belong to period 3, and so on. So the number of shells also tell you the number of, that is the period that element belongs to. So take note, the number of shells tell you the period. Why the number of electrons in the outermost shell tell you what? The group. If you have 2 electrons in the outermost shell, it means that that element is in group 2. If you have 3 electrons in the outermost shell, that element is in group 3. So number of electrons in the outermost shell tell you the group, while number of shells in the electronic configuration of an element tells you the words, the period. Take note of that. Right. Now, let's move. So as you go down the group, the shells, number of shells keep increasing. That is why the atomic size or radius keep increasing down the group. It increases down the group. As you go down, the number of shells keep increasing from 1 to 2 to 3 to 4 to 5 to 6 to 7. And as the shells increasing, the size of that atom keeps increasing. Right. So now, the other 3 are ionization energy. Ionization energy. Okay. Electronegativity. Electron affinity. I would have taken time to explain this so you don't cram them. Notice that it's very easy for me to remember because I don't cram them. I understand the concept. These ones increase across the period and decrease down the group. These ones. Right. Ionization is the tendency of an energy to, the tendency of an atom to turn into an ion. Right. Electron affinity. Affinity means love. Electron affinity is like the love of electron. Alright, love for electron, to attract electron. That's energy released to attract electron. While ionization energy required, alright, to ionize. And so energy required, what does that tell you? If energy is required, that means energy is absorbed. That means ionization energy is endothermic. Electron affinity is what? Exothermic. Is energy released when an electron is attracted. Right? Electron affinity, attraction of electron when there is a gain of electron. Electronegativity, the tendency of an atom to turn into a negative ion. That's electronegativity, and it increases across the period because as you move from left to right, you move towards the non-metals which are negatively charged. Alright, so these are the periodic properties that increase across the period, and when you go down the group, they decrease. So take note of that. They usually ask them. Alright. So also know that group 1, 2, 3 metals, they are electron donors, because when they lose electron, when they donate electron, they will not have positive charge, so they are electron donors. While non-metals are electron acceptors, because when they accept electron, they become negatively charged. So that's another important point to take note of in periodic table. Now let's quickly brush through electronic configuration. I'll talk about some of the things they used to ask you in electronic configuration, and we'll say goodbye to that. We'll have paramagnetism and diamagnetism, right? Um, let's do this. Okay. Okay. Yeah, a question like, how many unpaired electrons are in fluorine? This is a common JAMB question. How many unpaired electrons are in fluorine? How do you answer this question? Use the concept of electronic configuration. Now, in electronic configuration, you make use of Aufbau's principle. So whenever you are doing it in the exam hall, always make sure that you draw the Aufbau's principle. That is 1 S. Now remember the S, P, D, F. S, P, D, F. Here. S, P, D, F. So 1 S, 2 S, 2 P, 3 S, 3 P, 3 D. 1 S, 2 P. So 4 S, 4 P, 4 D, 4 F. Then write this in order. 3 P, 3 D, 5 S, 5 P, 5 D, 5 F. It continues in that order actually. 6 F, 6 P, and so on and so forth. They also have G, H, I, E, F, G, H, I. But we don't have like S, P, D, F, G, H, I. But for your level, stop at F. Right? Where this goes like this. I would always remember that. Alright. What does this tell you? It tells you that in the arrangement, 1S will go first, followed by 2S, followed by 2P, followed by 3S, followed by 3P, followed by 4S, followed by 3D, then 4P, then 5P, 5S, then 4D. So it depends on how long the elements are given is, like the atomic number. But for most of the times, you always stop around this side. Right? Most of the times, they can't really give you elements that are much more, that have much more atomic numbers to start finding the electronic configuration for your level anyway. But I'm just showing you how it is. This is what we call Aufbau's principle. This is what we call Aufbau's principle. Okay? So if you are asked, how many unpaired electrons are there in fluorine? So first of all, you ask yourself, what is the atomic number of fluorine? Fluorine is the 9th element in the periodic table. So the atomic number of fluorine is 9. So you write it, fluorine, 9. So now, do the electronic configuration of fluorine. It's going to give you what? 1s, 2. Mind you, S will have maximum of 2, P will have maximum of 6, D will have maximum of 10, and then F will have maximum of 12, 14, sorry. So S will always have maximum of 2 electrons, P will have maximum of 6 electrons, D will have maximum of 10, F will have maximum of 14. That's addition of 4 each, starting from 2. The first one is 2. If you add 4 to 2, you have 6. If you add 4 to 6, you have 10. If you add 4 to 10, you have 14, and so on. So 1s2. After 1s, you have 2s. 2s2, because s will always have maximum of 2. After 2s, you have 2p. 2p6. 6 plus 4 is 10. That means we need 2p5 here. Right, so this is the electronic configuration of fluorine. But the question says how many unpaired electrons. So we have to focus on this last one. We have to draw the orbitals, represent the orbitals of the p sublevel. Mind you, the s sublevel. Let me wipe this off. The s sublevel has 1 orbital. The p sublevel has 3 orbitals. The d sublevel has 5 orbitals. 1, 2, 3, 4. The f sublevel has 7 orbitals. Okay. So 1, 2. So this is 0. Call them -1, 0, 1, -2, -1, 0, 1, 2, -3, -2, 1, 0, 1, 2, 3. Don't worry about these numbers. You don't need them now. During post-UTME, we'll explain it because you need it in 100 level. But don't worry about it. What I want you to understand is that S has 1 orbital. Orbital is the region where electrons are found. P has 3, D has 5, F has 7. Now, since P, we are dealing with P, so we are going to draw 3 boxes. I'm going to draw 3 boxes, right? Now, inside these 3 boxes, I'm going to fill 5 electrons. But according to Horn's rule, electrons will fill singly before pairing. So if you want to fill the 5 electrons, you have to fill singly. And while filling singly, the first one will always spin upwards, while the second one will spin downwards. So the first one, this is 3. We have filled 3 electrons. It's remaining 2. So I would have used a different thing for this. Let me redo this so you see it very well. These are the first 3 electrons, the 4th one, and the 5th one. So this is the P5 electron being represented. And the question says, how many unpaired electrons are in fluorine? What is the answer? 1. Unpaired means something that is not 2. Pair means 2. This is a pair of marker, right? This is a pair, right? A pair is something 2. This is a pair. Now, this is a pair of electrons, a pair of electrons. This is 1 pair, so it is unpaired because it doesn't have a pair. So the question says, how many unpaired electrons are in fluorine? The answer is what? 1. The answer is 1 unpaired electron. This is a popular JAM question. So in case you see a question like that or something's related, you'll be able to know how to tackle it. Alright? So that's about electronic configuration. I believe you should know this. Any elements you are given, just follow the Gauss principle and write it, and you get the electronic configuration. If you're asked how many unpaired electrons, you know how to do it. Now, there's what we call diamagnetic and paramagnetic substances. They don't usually ask it, but I think they've asked it once in 2003 JAM pass question, right? So I'll just show you. Paramagnetism, diamagnetism. Diamagnetism. So this is just unpaired. Paired. So whenever you do electronic configuration of an element and it has an unpaired electron, then you say that that element is what? That element is what? Paramagnetic. But if you have something like P6, that is neon. That is for neon. You now have 6 here. Then that element is said to be what? Diamagnetic. So once it is fully paired, it is di for 2, fully paired, diamagnetic. Para, set for opposite direction. Alright, that's literally like what para, more like trans anyway. That's paramagnetism. Right, so that's it. There are deeper meanings to it actually, but this is what you would be required of, or this is what is required of if they ask it in chemistry in terms of electronic configuration. This is what is required of you. I believe I've kind of summarized electronic configuration to an extent. And let me quickly talk about bonding. Let's quickly talk about bonding. Bonding, bro. Now in bonding, we have ionic / electrovalent. Electrovalent. We have covalent. We have dative. Dative is also known as what? Coordinate covalent. Now, this is usually between metals and non-metals. Usually between metals and non-metals. I don't say always, but usually between metals and non-metals. For example, the bond found in sodium chloride is what? Ionic bond or electrovalent bond. That is, this kind of bond is found when an electron, an atom transfers electron. So take note of that. That's another question they might ask. Which of the following bonds is formed when an electron? Once you hear transfer, the key word they usually use in German, transfer. Once you hear transfer, just be looking for electronic. Let's just be looking for electrovalence or ionic. Alright, transfer of electrons. So transfer of electrons. Once you hear transfer of electrons, look for ionic and peak. Alright, so because here, you know when you show transfer of electrons, that means one is transferring electron to another element that is accepting. That element is usually the metal. That's why I say it's between metals and non-metals, because metals are electron donors. They donate, they transfer electron. While non-metals are electron acceptors. So when a metal donates or transfers electron, the non-metal will do what? To accept it. The non-metal will accept that electron. Now, covalence. For covalence, we have the key word there is sharing. Sharing of electrons equally. Let me put usually between non-metals. Equal sharing of electrons usually between non-metals. Example, ammonia. That's a good example. We always see ammonia. Organic compounds. The bond in organic compounds is usually covalent. This is an organic compound. Covalent bond. Ammonia to carbon dioxide. Covalent bond. Because most times this is a non-metal, this is a non-metal, this is a non-metal, this is a non-metal. Most times when you have two non-metals together, they usually contain covalent bonding, right? Because they share electrons equally. The 5 electrons in the outermost shell here will combine with the 3 electrons in the outermost shell of each of the hydrogen. Hydrogen has 1 electron in its outermost shell. There are 3 here, so that means we have 3 electrons in the outermost shell of hydrogen. Nitrogen has 5. The 3 plus 5 will combine to give you 8 for this. And then each one here will combine with 1 from here to give you what? 3. Each one here from hydrogen will combine with each one of the 1 from nitrogen. Let me do it for you. Let's do the share so you see it. This is nitrogen. The central atom is the one that is less, which is nitrogen. So it has 5 electrons in its outermost shell, right? So hydrogen will be distributed. The 3 hydrogen atoms. You have 1, you have 2, you have 3. Hydrogen itself has 1, 1, 1. Now, they need to be stable. I told that the main essence of compounds, elements combined to form compounds, is for stability. When this combines with this will combine with this, and this will combine with this. What do you think will happen? Notice, if hydrogen combines with this electron, this hydrogen is already stable. It has duplet structure. Likewise this one, likewise this one. And what happens to nitrogen? Nitrogen has originally 1, 2, 3, 4, 5. They are sharing it equally. The 5 plus 1, 2, 3 from hydrogen that they are sharing makes it what? 8, which is what? Octet. So in turn, nitrogen now has octet structure. Hydrogen now has duplet structure because they are sharing them together. So that's what we call covalent bonding. Now, a question might come in this form. How many unpaired electrons are in ammonia? This is a very popular question. How many unpaired electrons can you see? 1, not 2. 1. Sorry. Yes, 1. This is a pair. No, not unpaired. This electronic configuration has entered my head. The question usually comes in the form, how many lone pairs? How many lone pairs or lone pair of electrons are found in ammonia molecule? This is ammonia. I just showed you. The answer is what? 1. This is a lone. A lone because it is not part of the bonding. These ones that are part of the bonding are called bond pairs. The ones that are part of the bonding are called bond pairs. The one that is not part of the bond is called lone pair because it's alone. It's not bonded to anything, and it is a pair because it is 2. A pair means something 2. Alright, so the number of lone pairs in ammonia is 2. Another good example is water. Water is another good example that they usually use in the exam of a covalent compound. And they usually ask number of lone pairs in water too. So I'm going to show you that one and we move. So water is H2O. What's the central atom? Oxygen. The one that is lesser in number of molecules is the central atom. In the former one, the nitrogen is the center atom because you just have one nitrogen here. Right, that's the central atom. What's the oxygen has 6 electrons in its atom shell. So we have 1, 2, 3, 4, 5, 6. Right. Now, we now talk about hydrogen. So we can attach the hydrogen here. Attach hydrogen. These are the 6 electrons in the atom shell of oxygen. This is the one for hydrogen. Right. So what will happen? They will combine. They will share. Remember, oxygen has 6 plus 1, 7 plus 1, 8. The 2 is sharing from hydrogen, makes it attain stability, 8 electrons. Hydrogen 2 is sharing 1 with oxygen, making it duplet. Hydrogen is sharing 1 with oxygen, making it duplet. That is to say that a bond contains 2 electrons. This is a bond, it contains 2 electrons, 1 and 2. Right, take note of that. Every bond contains 2 electrons. Now, how many lone pairs are in water molecule? Count with me. 2. So water molecule has 2 lone pairs, not 4. Don't go and say 1, 2, 3, 4. No, this is a pair. A pair means something that is 2. This is a pair. We call it 1. This is another pair. We call it 2. They are not part of the bonding. So they are alone. So they are known as lone pairs. Alright. So water has 2 lone pairs. This is a typical JAMB question. So take note of that. Another question they used to ask from water is, what is the shape of water? The shape of water is V-shaped or bent or angular. You can see any of these 3. Alright, shape of water is bent, shape, or V-shaped or angular. Alright. What's the shape of ammonia? I'm going to tell you. So take note of this, write these up. These are giving you important JAMB questions here. How many lone pairs of electrons are in water molecules? 2. What is the shape of water molecule? V-shaped or bent shape? What type of bond is found in water molecule? They are sharing. Are you there? Though we also have hydrogen bond. The bond between each hydrogen atoms is known as hydrogen bond anyway. But they rarely ask that. Yeah, but when we talk about hydrogen bond, it's just the bond between hydrogen atoms, right? Now, let's move. Read the shape of this. Okay, I'll talk about that. The shapes later. I'll talk about shapes later. Let me finish dative. Dative bonding is found when you have one atom doing the sharing. One atom is just sharing. The guy just they share. Alright. When one atom is the one sharing, and that's different between covalent and in covalent, the constituent atoms share equally, but in dative or coordinate, only one atom shares. A good example is ammonium ion. This is a good example they usually use in JAM. All these complex ions that have ions, right? Like they are complex salts. They usually have this coordinate covalent bond in them, right? So that's a good example you will see in your exam. Now I was talking about the shape of ammonia. Ammonia is trigonal pyramidal. So ammonia is trigonal pyramidal. pH 3. That's phosphine. This is phosphine. Rotten fish smell. Trigonal pyramidal. BH3, boron, that's boron trifluoride, trigonal planar. BF3, trigonal planar. I want to tell you something about trigonal planar and trigonal pyramidal. Very simple. Once you have an element bonded to 3 atoms, it's either going to be trigonal planar or trigonal pyramidal. Now, how do you know the one that is planar and the one that is pyramidal? If the elements if the single element is a group 5 element, if the single element is a group 5 element, then it is pyramidal. If the single element is a group 3 elements, then it is planar. This is a group 3 elements, planar. Group 3 elements, planar. Group 5 elements, pyramidal. Group 5 elements, pyramidal. Nitrogen is a group 5 element. Phosphorus is a group 5 element, so the two have pyramidal. Boron is a group 3 element, so it will have planar. Then, regardless of this is boron trifluoride, boron trihydride, or boron hydride. Alright, so that's about these ones. Into that shape, please ask you shape of organic compounds. Can I clean this? I've basically exhausted this. I've seen what I wrote. Don't forget the bond angle of water is what 104.5 degrees. The bond angle of tetrahedral molecules like this methane is 109.5. Trigonal planar 120. Linear 180. Linear is on a straight line. Linear means line, straight line. So when you have a linear curve, it is a straight line graph. So when something is in linear straight line, angle on the straight line is 180. Now, when you say trigonal planar, it means a plane divided into 3 equal parts, more like a circle divided into 3 parts like this, right? Like a type wheel of a car. Now, if you divide the circle into 3 parts, what are you going to have? Angle on the circle is 360 degrees. Angle on the circle is 360 degrees. So each part will have 120. That's why trigonal planar molecules will have 120. So these ones will have 120. The tetrahedral 109.5. Alright. Same with this ammonia too, actually. Because ammonia has a lone pair, making it to have a tetrahedral kind of nature. So ammonia will also have the same bond angle. Right. Why trigonal planar molecules will have 180. Take note of these bond angles. These are important jam questions that you can always use and pick your 2.5 marks and run away. Alright, so take note of these things, write them down while we proceed. I'm going to give you one more kind of question from bonding that they usually ask, and maybe we'll look at solubility small. Look at solubility small, and look at stoichiometry small, and look at organic chemistry, gas laws small. There's a lot to cover If you look at, if we can do solubility, stoichiometry, gas laws, and a bit of organic chemistry, just important things, how to name compounds, because they will surely ask you to name compounds, and we'll call it a night. We've tried, right? So let's get this down. Okay, it is important you know this is 107 degrees. This is 109.5. This is 107 for ammonia. Anyway, ammonia is 107. They used to ask it the bond angle of ammonia, right? So I'll be wiping it off in 30 seconds. So let's move. Now, as a question they used to ask in this form, this is not the exact kind of question, but if you have a question like, given that an element has a charge of, okay, let's say given two elements, P and N, where P has +2 charge and N has -3 charge. And the question says, what kind of bond is formed when these two elements come together? Now these are imaginary elements. Let me just use X and Y so I not think let me just use X, Y. These are imaginary elements, and they tell you that the first element has +2 charge, second element has -2 charge, and they ask you what kind of bond is found between these two. Now, first of all, there are two ways they used to ask this kind of question. There is a type they used to ask about the bond. I'll talk about that one first. Now, what happens to, or what do you know of an element that has a +2 charge? It is a metal. Metals are positively charged. Non-metals are negatively charged. So the kind of bond that is most likely to be present when these two react, when these two elements come together to form a compound, is what? Electrovalent or ionic bond. Ionic bond or electrovalent bond, because the two of them are what? They are a combination, they are from metal and non-metal. I told you that ionic bond is usually formed from metals and non-metals, right? So ionic, that's one kind of way they use ask this kind of question. Another way they use ask this kind of, if you check your past question, you see this thing I'm talking about. Another way they use ask this kind of question is they will say two elements have this kind of charge. Two elements X have a charge of +2 and Y has a charge of -3. And now ask you, what is the correct formula of the compound formed when the two elements react? So I've taught you that already. What are you going to do? Do your exchange of radicals. They say the first element has a +2 charge, second element has a -3 charge. So you do your cross multiplication. X times 3, x3. X times Y. Sorry, Y times 2. Sorry, Y times 2 give you what? Y2. Mind you, I wrote X first before Y because X has a plus charge. So X is most likely a metal. And I told you we write the metals first before the non-metals. So because X has a positive charge, it's most likely going to be a metal. So we write it first. Right, good. Now in the options, you might see something like this in the options. Option A, option B, option C, option D. Now, if you're a good science student, you know that this is out. Let's use a black marker here. This is out and this is out because it's starting with the non-metal. So the non-metal cannot come first. Now you now come to this, it's between this and this. You now check, do your exchange of radicals. If they exchange radicals, X will go to 3. X will have a subscript of 3, which is this, and not this. That means this is wrong, and this is our correct answer. Check your past questions. You see questions like this. Very, very simple questions that you can use to get your 2.5 marks. So that is basically what they will ask you on chemical combination and shapes of molecules and bond angles. I've kind of combined them together now. All right. So let's move. Now, solubility. This is just the formula I want you to know. Remember that N is equal to CV from stoichiometry. From this, that's where you get your solubility formula. Use it to solve your question. Most times you see some questions on solubility like that. So moles equal to no. N is equal to CV. Alright, moles is what? Mass over molar mass. Or I like to use capital M, but some people used to confuse it. So let me use this. Molar mass. Let's use double M to represent molar mass. Alright, is equal to concentration times V. But before we do that, concentration is equal to what? N over V. If N is equal to CV, that means C is equal to N over V. If you make C series of formula, but mole is mass over molar mass. So substitute it here. C is equal to what here? Mass over molar mass divided by V. Concentration is mass over molar mass divided by V, which means concentration is equal to mass over molar mass times 1 over V. When you change the division sign to multiplication sign, you multiply by the reciprocal of what you have here, which is 1 over this. Right, because we change the division sign to to multiplication sign. Alright. Now, this is the formula for solubility. This formula is what you are going to use to solve questions where volume is in dm cube. Where volume is in dm cube. Or you can use the formula. This concentration can be used as a solubility. So if you like, you can call it S. Solubility is equal to mass over molar mass. Mass over molar mass times 1000 divided by volume cm cube. So notice something. There is 1000 here, there is 1000 here. dm cube or liter. 1 dm cube, which is equal to 1 liter. 1 dm cube is 1 liter, so you can have it in liter or dm cube. Or if you have, most times their volume is usually in centimeter cube when you are calculating solubility. They say if the mass of a sodium, okay, let me give you this question. They say if the mass of sodium if the mass of sodium chloride salt is 40 grams in a solution of 500 cm cube, what is the solubility of the salt? Simple. Mass. Sorry. What is the solubility of the salt? So it's a mass of the substance is what? 40 grams, right? 40 grams. Volume is what? 500 cm. How do you get the molar mass? They mention sodium chloride, so you get the molar mass yourself. The molar mass of sodium is 23. The molar mass of chlorine is 35.5. So when you add them, you are going to have 58.5. We're going to have 58.5. So the solubility of this salt will be mass of the salt divided by molar mass of the salt times 1000 divided by the volume given to you, which is in dm³. So when you multiply using your calculator in JAM, the calculator will be on the screen. So what you just have to do, simplify further if possible before you start multiplying, so it will be easier for you. If you do this, you're going to have 5 divided by 30 is 2. Right, 40 times 2 is 8. 80 divided by 58.5 will give you the solubility. So you can now go ahead and press in your calculator 80 divided by 58.5 instead of pressing 40 over 58.5 times 1000 over 500. No, you have to try as much as possible to make your things fast, right, in the example. So if you do this, 1000 divided by 500 is 2, right? 2 times 40 is 8. 80 divided by 58.5, that will give you an answer, right? So that's basically it about solubility. There's no big deal there. And this is in turn what you can still use for stoichiometry related problems, which I'll add more for you, and we move. We are trying to be as fast as possible. Some of you will soon start sleeping, so latest by 1, 2 we should be rounding off so that you go and rest. And likewise me. Alright, all of us are students. Alright. Sorry. So for stoichiometry, master this formula. If you watched my video on stoichiometry, I dropped this formula, but if you didn't, after this session, please go and watch it. So you see like a breakdown, right? So you have moles is equal to mass over molar mass. I like to use capital M. Mass over molar mass to moles is equal to concentration times volume. Molar concentration times volume. PV is equal to nRT. I explained how to use R, this R. That is when R can be equal to 0.082 or R can be equal to 8.314. So I explained when to know how to use it. In particular, R is a constant, molar gas constant. So it's being used depending on the value of your PV. So go and watch the video, that video I dropped. Right. Subsequently, by God's grace, we'll try to do more videos when we have time. But go and watch that. It explains all this very well for stoichiometry. I don't need to waste much time on that again. Alright. You have CAVA over NA is equal to CBVB over NB. This is for neutralization reactions, when you have concentration of acid, volume of base, and so on and so forth. You also have mass conc. Molar conc is equal to mass conc over molar mass. Alright, so and so many other formulas that can be derived from this. From this, you can have the formula for density and so on and so forth. So when you know this formula and how to combine them, also you have the moles. Number 6, this one is important. Let me write it here. moles is what number of atoms over Avogadro's constant, where Avogadro's constant is equal to 6.02 times 10 raised to the power 22. 6.02 times 10 raised to the power 22. So when you are giving the moles of a substance, or even if you are not giving, maybe they give you mass and they mention the particular compound. So use the particular compound they mentioned to get the molar mass of the compound. Then divide the mass by the molar mass to get the moles. Then multiply the moles by this to get the number of atoms present. So they can ask you, how many number of molecules are present in 4 grams of magnesium chloride? So you know what to do. Or how many number of atoms are present in 4 grams of magnesium chloride? So this N can be number of atoms, number of ions, or number of molecules. And once you hear number of whatever, number of blah blah blah, you use this formula. All right, it's very straightforward. Use this formula, get the moles, multiply the moles by this, you get the number of what that thing they're asking you about. So that's it. Now for gas laws, I believe we already know gas laws. Boy's law. Boy's law. Boy's law. Boy's law says that the volume of a given mass of gas is inversely proportional to its pressure. That means volume is equal to K over P. That means K is equal to PV. Right? If you make K the solution formula, K is equal to PV. That means P1 V1 is equal to P2 V2, which is equal to P3 V3, and so on. Alright. Well, so we basically use this. That is, if you are comparing two pressure and two volume. Maybe they gave you 3 out of the 4, so you use this to find the 4th one. If you are looking for volume V2, make V2 the solution formula. That will give you P1 V1 over P2. Right? Very simple. Now, for the graph of Boy's law, right. The graph of Boy's law is usually like this, where you have P against 1 over V is a straight line graph, or you have P. Sorry, I'm not drawing this very well. P against V, you have something like this. Usually have something like this, A and B, as the graph of Boy's law. Alright, so that's basically that. You can put the graph and ask which of the following graphs illustrates Boy's law. Take note, if it's a curve like this, it means that as volume is increasing, as pressure is increasing, this is increase of pressure. As the pressure is increasing, the volume is decreasing, and vice versa. Alright, as the pressure is decreasing, the volume is decreasing, the volume is increasing, like this. So, and as volume is decreasing, the pressure is increasing. Do you understand? So they are inversely proportional. Volume is inversely proportional to pressure. That means as pressure is increasing, volume is decreasing, and as volume is increasing, pressure is decreasing. So anything that is happening to one, the opposite of it will happen to. That's why it's reciprocal of the other. That's what is happening here. If you go like this, if you go down, you see that you are going down from pressure. So pressure is going down, pressure is decreasing, and then you are going to the right. Look at it. This is a graph, actually. So if you have a graph, in a graph, you usually have something like this, right? So let's say this is 1, 2, 3, 4. This is 1, 2, 3, 4. Look at it. As I'm going down the graph, the pressure is what? Decreasing from 4 to 3 to 2. It's decreasing. And as you're moving towards the side, if you're coming down like this, the pressure is decreasing, and what happens to the volume? It is increasing. If you say let it go like this, the volume is decreasing, and what's happening to the pressure is increasing. That's Boyle's law. If a graph of PV will give you this, but a graph of PV will never give you this. This is a graph of P against 1 over V, or so these are 3 possible graphs of Boyle's law. A graph of 1 over P against V, or a graph of P against 1 over V, or a graph of P against V in this form. So a graph of this against this, or this against this, will give a straight line graph. Because as the pressure increases, the reciprocal of the volume will increase. But the volume itself will decrease, but the reciprocal of the volume will increase. Do you understand? Volume is directly proportional to the reciprocal of the pressure. Volume is directly proportional to the reciprocal. So as volume increases, the reciprocal of the pressure increases. But as volume increases, the pressure decreases, because these are in opposite sides. But this, the whole of this and this are in the same side. Do you understand? I hope that makes sense. So that's it about Boyle's law. Charles' law. And mind you, when you are using Boyle's law and Charles' law, make sure that it's not a must to, most times it's safe to just convert your temperature to Kelvin while solving. It's safe, but it's not usually a must when they are dividing through, because they will still cancel out. But to be safe, just convert, to avoid causing confusion for yourself, just convert to Kelvin, right? But I'll show you that. So Charles law says that the volume of a given mass of gas is directly proportional to its temperature, provided that what remains constant, the pressure remains constant. The one that is not mentioned here is constant. And they said the volume of a given mass of gas. So that means mass is constant. So there are two things that are constant. The volume of a given mass of gas. So that means a fixed mass, a constant mass. Do you understand? So in Boyle's law, mass and temperature are constant. In Charles' law, mass and pressure are constant. So that means V is equal to KT. K is equal to V over T. So we can have that V1 over T1 is equal to V2 over T2. And let me use dots, dots, dots. Alright. So K is equal to V over T. From here, if you remove the proportionality sign, add an equal sign, you introduce a constant. The constant is equal to V over T, which means that you can use the constant to compare two or more of this. Right. So volume is directly proportional to temperature. So you can have volume here and temperature here, or you can have temperature here and volume here. They are the same thing. Anyhow they put it, is the same thing. Right? It's the same thing. Now there is one they used to draw that will cut through like this. You have minus 273 degrees Celsius. Once you see the graph, know that it's also a graph for Charles' law. Alright. This temperature is known as what? Absolute temperature. This is known as absolute temperature, right? It is called absolute temperature. That's okay, or 0 Kelvin. So note that there's nothing like 0 degree Kelvin. There's nothing like 0 degree Kelvin. All we have is Kelvin. Kelvin is the name of person. It's not a degree, right? So 0 degrees Celsius or 0 Kelvin. So this is known as absolute zero temperature, or we call it absolute temperature or absolute zero. You can call it absolute zero temperature, absolute temperature. Right? It is absolute. When you know the for the mathematics students, when you have something like this is known as absolute value of -1. The absolute value of -1 is what? So absolute value means that it cannot have a negative sign in front of it. Even if it has a negative sign, the fact that it's absolute. This sign is absolute sign. The fact that it is the absolute value of it will nullify the negative sign. What it means is that Kelvin temperature can never have a negative sign. Take note of that I said that Kelvin temperature can never have a negative sign. That is why it is called the absolute temperature. The Kelvin temperature is called the absolute scale. The Kelvin temperature is called the absolute scale, right? Because it does not have a negative sign. It's nothing like -1 Kelvin, but you can have -1 Celsius, but you cannot have -1 Kelvin. It is not appropriate. So for your level, just know this. There are other formulas, but just know this. So if you want to convert from Celsius to Fahrenheit, use this. So if you want to convert from Fahrenheit to Celsius, you make the C, the series of the formula, right? And if you want to convert from Fahrenheit to Kelvin, first of all, convert from Fahrenheit to Celsius using this. Then now use it to convert to Kelvin using this. Do you understand? So these are important for your level, right? This is actually the same thing as yeah, the same thing, right? 9/5 is 1.8. All right. Okay. Now, the formula I want to drop now is coming in. I can clean this, right? I can clean this. You have to be fast with your writing, please. I want to end by 1 or 2 at most. In electrolysis, Okay. Um, so these formula you can use them in electrolysis, right? Where I give you mass and now for this. You see these 6 elements, master them in stoichiometry. Sorry, in electrolysis, they don't play with these 6 elements. Know their mass numbers. Mass number of copper 2 ions. Mass number of copper is 6, for zinc is 65. Know their ions plus. These charges are important. That's what you use to get the electrochemical equivalence Z. Some textbook will use E for electrochemical equivalent. Alright, so if M is equal to electrochemical equivalent times charge, quantity of charge, charge itself is what? Current times time. So if you substitute charge, you are going to have M is equal to Z IT. Since charge is current times time, you have this. This is molar mass. When you are looking for molar mass, and you have mass, you have charge on an ion, that's charge on an element. You have Faraday's. 1 Faraday is equal to 96,500 coulombs. Take all of that. So you add that here, add this here, divide this, you get the molar mass of that compound. So they give you the mass, multiply the mass by the charge, which is 2. If you are looking for copper, and let's say they give us the mass of copper, multiply the mass of copper by the charge of copper, which is 2. Multiply by this, divide by current times time. Or they will give you the quantity of charge to be so and so coulomb. Quantity of charge is also measured in coulombs. So coulomb will cancel coulomb. Alright, and you've left it this. Alright. This is actually an equivalence of this. Q times M is QM. Q is equal to M over M divided by M over M is equal to N. You get, so they are the same thing. Just that it's abridged. So when you have moles times charge times this, you get your quantity of charge directly. That's how you get Q. With this, you get your Q. You can substitute your Q here to get your M. Right here. Now, if you don't know Z, you can use this to find your Z. For instance, if you want to find the Z of copper, it will be what? Mass of copper times this times the charge. Let me take it. If you don't have, sometimes they might not give you the electrochemical equivalence, right? But you have to find it yourself. It's easy to find, right? Copper is, if you are looking for copper results, molar mass of copper divided by 96500 times 2. For copper, this is Z. For copper, for zinc, is equal to 65 over 96500 times 2. For aluminium is equal to 27 over 96500 3, and so on and so forth. You understand? If you check these things online now, you see that the value you get here, check for the electrochemical equivalent of copper online. You notice that what you get is equal to what you get here when you punch this calculator. Check the electrochemical equivalent of zinc. You see that it will be approximately equal to this. Right, so when you are not given in the question, use this and get your answer. Do you understand? Mind you, you have to press the denominator first to avoid pressing 65 divided by 96500 times 2. It might give you, it depends, you know that calculator is not scientific calculator. So when you are dealing with something like this, you have to be careful. Do the denominator first, keep it one side. If you do the denominator first, you're going to have 193000. Right? So you now divide. You see, I've done it so much that I even know what it is. You now divide 65 divided by 193000, 64 divided by 193000. Notice that the electrochemical equivalents of this and this are very, very close, because this is just 64 and 65. So it will give 0.003333 or something like that. Do you understand? Yeah, so that's basically, make sure you do the denominator first, keep it, then you now divide the numerator by the denominator, because of that jam calculator, to avoid getting a wrong answer when you know what you are doing. Do you understand? Good. Now they're not really asking that, that's in physics. Right, so are we good to go? Let me give you 30 seconds for this and I'll wipe it off. 30 seconds, 30 seconds. Let me leave I'll be the shaker. 30 seconds and we move. Alright, let's go. Alright. Should we talk about acid, base, and salts? Is there anything much? They don't usually ask it like that. Acid, okay, neutralization reactions. Okay, let's just briefly talk about acid, base, and salts. I try to know the kind of questions they ask. They might ask calculation as a neutralization reaction is a type of reaction between acid and base to form salt and water only. So they can ask that kind of question. Yes, it's a jam pass question. Which of the following is a type of reaction between an acid and a base to form salt and water only? It is neutralization reaction. Example: acid plus base to form salt plus water. All right. So guys, sorry there was a technical challenge there. So now I was just trying to explain it, just briefly talk about acid Arrhenius acid, Bronsted and Lowry acid, Lewis acids, and bases before the technical issue came up, right? So this is just it. Arrhenius definition of an acid says that an acid is a substance that dissolves in water. Let me take that again. To produce hydroxonium ion or hydrogen ion. A base is a substance that dissolves in water to produce hydroxide ion. Bronsted and Lowry said that an acid is a proton donor. A base is a proton acceptor. Proton. This hydrogen, when we hear proton, just know that we're talking about hydrogen plus, hydrogen ion. Lewis, electron pair donor. Acid, electron pair acceptor. So these are definitions of acids and bases according to these scientists. Right, so please pin them down before we continue. Right, I think the concept of Bronsted and Lowry definition brought about the concepts of conjugate acid and conjugate base. So note, they can ask you in your jam, a conjugate acid defines conjugate base or by its corresponding acid by what? Or base, sorry, by what? By a proton. Alright, so if you have something like this, no. Um, um, so if they ask, this is an acid base, salt and water actually, but because of the fact that the difference between this acid produce this salt, because the ion in the acid is what is found in the ion in the salt. That means if this is an acid and this is a base, this is a conjugate acid base, conjugate acid, conjugate base. Alright, so if this is an acid, it has the corresponding the difference between the acid and its conjugate base is what? A proton. Alright, and vice versa. The difference between an acid and its conjugate base is a proton. That's just a typical jam question anyway. Right, so that's about acids and bases. Acids are corrosive, bases are corrosive. Acids have sour taste, bases have bitter taste. Take note of this. These are physical properties of acids. Right, they might ask you. Alright. So I think you should have been done with this. Lewis electron pair donor, electron pair acceptor for acid. So you know how to do it in a tabular form for yourself. Okay. Now let's quickly talk about how to name organic compounds and we'll wrap it up for the day. Some of you are already tired, I can see that already. Alright. Before we talk about that, okay, well, let's just do it. Let's just do it for want of time because they will definitely ask you to name compounds in organic chemistry. In your chemistry, one of the questions you will see every year is naming. They like it, and it must come out. Naming of organic compounds. So let's just quickly do it. And the first rule in naming of organic compounds says identify and number the longest continuous carbon chain. Identify and number the longest continuous carbon chain. Let's go. So yeah. Now when drawing the structure of compounds, have it in mind that carbon is tetravalent. Carbon is tetravalent. That means it will attract 4 bonds. Right? Remember that periodic table I drew for you? The charge on carbon is -4, right? That's because the carbon is tetravalent. Oxygen is -2, right? Oxygen is divalent. Nitrogen is -3, right? Nitrogen is trivalent. Are we good? Sulfur is what? Divalent. Yeah. So now, let's go. Identify and number the longest continuous carbon chain. We are going to number these in different forms and see the one that is most appropriate. That's the green marker I'm looking for. Now, we number this in different forms. Using the blue ink, we said 1, 2, 3, 4, 5. This is continuous, but is it the correct numbering? Let's find out. Now, when we say number the longest continuous carbon chain, that is the first rule of naming organic compounds. Identify and number the longest continuous carbon chain. It means that when you are numbering, once you have branched, you cannot come back to that branch that you've left. So if I'm numbering, for instance, this red ink, using the red ink, you have 1, 2, 3. I cannot come back. I was going like this. And then I branched. Because of the fact that I branched, I cannot come back and continue in that former place I was going. That is no longer continuous. So once you have branched 1, 2, 3, you are no longer coming back to number this. That means if you are saying that 1, 2, 3 is the longest continuous carbon chain, which is not, because we have 1, 2, 3, 4, 5, which is the longest, which is continuous, and it is the longest continuous carbon chain. That means we have 2 longest continuous carbon chain. We can number 1, 2, 3, 4, 5, and we can also number 1, 2, 3, 4, 5. Now the question is, which one is the correct numbering? Since the two of them are the longest continuous carbon chain, which one is now Correct. So we've established that the red ink is wrong because it's branched. Even though it gave us carbon six carbon atoms, but it is not continuous. So the red ink is wrong. The black ink is also wrong. The black numbering is also wrong because look at the black number. You say 1, 2, 3, 4, 5, 6, which is also wrong, right? Now let's focus on the green ink and the blue ink. Right, the green and the blue. Okay, so let me check which of these is better. For the green ink, we numbered 1, 2, 3, 4, 5. For the green ink, sorry, for the blue ink, we numbered 1, 2, 3, 4, 5. Now, the second rule that you have to know, we've established what it means to number the longest continuous carbon chain. Now, the next rule is to number in such a, if there is a substituent, number in such a way that the substituent will have the lowest number. Write it down. Rule number one, identify and number the longest continuous carbon chain. Rule number one, identify and number the longest continuous carbon chain. Rule number two, okay, let me take rule number one for the last time. Identify and number the longest continuous carbon chain. Identify and number the longest continuous carbon chain. Identify and number the longest continuous carbon chain. Rule number two, if there is a substituent. So first of all, let me explain what a substituent is. A substituent is simply that particular part of the compound that you did not touch when you are identifying the longest continuous carbon chain. So we've identified the longest continuous carbon chain 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. That's the longest continuous with no branch. I did not say you should not branch, I'm just saying once you have branched, you should not come back to the branch you left. But at the same time, if you are branching, make sure that the only reason you are branching is to get the longest carbon chain. That is the only reason you can branch. But if you branch here 1, 2, 1, 2, 3, 4, 5, that means you can also branch like this because we'll still get 5 as carbon longest continuous carbon chain, right? But then, is it correct? We'll find out. So back to my rule 2. If there is a substituent, I've explained what a substituent is, the particular carbon you did not touch. So we numbered 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. We did not touch this particular carbon. That is our substituent. So if there is a substituent, number in such a way that the carbon bearing the substituent, this is the carbon bearing the substituent. So number in such a way that the carbon bearing the substituent will have the lowest possible number. Number in such a way that the carbon bearing the substituent will have the lowest possible number. Right? Good. Now, hold on. Right. Now look at this. If we check the green ink, we have 1, 2, 3, 4, 5. The substituent is on carbon 2. If we number from left to right. If we number from right to left, 1, 2, 3, 4. The substituent is on carbon 4. So which numbering are we going with? We are going with the numbering from left to right in this case because it gave us the substituent at carbon 2, which is lower than when we number from right to left and it give us at carbon 4. So our substituent is on carbon 2 from left to right, which is closer, which is shorter. The goal is to give the substituent the lowest number possible, right? So that the name of the compound will now become, this is 2 and this is methyl, right? CH3 is methyl, so we have 2 methyl. The longest continuous carbon chain is what? 5. 5 stands for what? Pent. Two methyl pentane. This space is too much anyway. So this is how to write it. methylpentane. Alright. I believe by now you should have known that methane starts. Okay, let me just give you, for the sake of those that might not know, let me just do that. After this will rest and other things will continue on the group chats. Alright. So C. Sorry. So when an atom has one carbon, the prefix will always start with meth. Right? So you can have methane, methyl, methanol, and so on and so forth, telling you that it has one carbon atom. If it's two, it's F. Right? Ethane, ethine, ethene, ethanol, and so on. Pro. 3. Boots. 4. Pens. 5. Hex. 6. Hex. 7. Ox. 8. None. 9. Dick. 10. From decimal. So Dick has to do it 10. Alright. So this is fundamental thing you need to know. Just in case you don't know, I just wrote it. I believe you should have known it by now. Alright. Okay, I've given you 2 rules. Now, third rule you need to take notes of is, if there is a functional group present, number in such a way that the functional group will have the lowest possible number as well. Yeah, number in such a way that the functional group will have the lowest possible number. For instance, now looking at this compound, how do you name? Identify a number the longest continuous carbon chain. If there is a substance, number in such a way that substance have the lower number. But even when there is a substance, you treat the functional group first before the. So now there is a functional group. What's the name of the functional group? Hydroxyl functional group. This is the functional group of alkanols. That means our name should end with all, because this is an alkanol, because it has an OH functional group. The OH tells us the parent name of the compound. Alright, so since there's a functional group, the name should end with all. right? So let's give our two possible numbers by identifying and numbering the longest continuous carbon chain. We have 1, 2, 3, 4, 5, 6. Notice something. I was going like this. I branched. I did not, there was not a point where I had to like go back and start going where I branched. And I was going like this. I turned like this, going straight to. So you can see go down, see go left. Go. The goal is once you have turned, you are not going back to where you turned from again. Otherwise, it is no longer continuous. Let's number from the other way. Now, in both ways, we got 6, 6 as the longest continuous carbon chain. Now, the question is, which of the numbering is most appropriate? Look at the first numbering with red ink. The OH was on carbon 4. Look at the second numbering with blue ink. The OH was on carbon 3. What does that tell us? It tells us that we are going to make use of the second numbering with blue ink because that gave us the lowest possible number for the hydroxide group, which will make the name of the compound to become, the hydroxide group is on carbon 3. The longest continuous carbon chain is 6. So 6 stands for hex. This is hexane 3-ol because the OH functional group is on carbon 3. The longest continuous carbon chain is 6. So hexane, instead of saying hexane, or you say hexanol because it is an alkanol. But instead of just saying hexanol, you put the number where the ol is found, that is the OH group is found, which is on carbon 3. So hexane, instead of saying hexanol, you say hexane 3-ol, telling that the OH group is on carbon 3. Alright? Now, I'm going to talk about how to name esters. They used to ask it. How to name esters. So for naming esters, you name the R prime first. Name this R prime, then you now name this. You join the other number of carbons here. Alright. So let's go. Name the methyl group after the COOH. That's what we are going to look at. If there are C2H5, whatever thing that is after this, you name it first. This is what methyl. Then count the remaining number of carbons. 1, 2, 3. 3 is for what? Prop. This is an alkanoid, ester, alkanoid, so propanoids. Methyl after the COO group. Then count the number of carbons remaining. 1, 2, 3. 3 is for what? Prop. What? Propanoids, because this is an alkanoid functional group. Right? Good. Let's take maybe 1 or 2 more examples. If you have once again, name this. This is 2 carbon atoms. That's ethyl. 1, 2, 3. There are 2 carbon atoms. So 1, 2, 3. Ethyl propanoid. Right? Good, 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 good. What about this? So they can also call it diethyl ester. That's ethyl at the left hand side, ethyl at the right hand side, ester at the middle. So diethyl ester. This is a trivia. This is not an IUPAC name. If they ask you for IUPAC name, this is the IUPAC name. The only time you can call it this or go with this if there is not, if this is not in the option. But this is the IUPAC name. This is the trivial name. All right. Now this is what we call our carboxyalkane and ether. This is an ester. Ester has COO. Ether has O at the middle. Ether. Ether has O at the middle. Ester. Ester has COO at the middle. Right. So in the same way, if you name this, you're going to have methyl. But we'll call it this ether. Their family name gong is alkoxyalkane. Alkoxyalkane. So why naming them? Instead of saying methyl, we say methoxy. Methyl, methoxy. Then we will no longer call it methyl, we call it methane. Because that's how to name them. So this is methoxymethane, even though methane is CH4, but we call this methane. If we have what will it be? Methoxyethane. Because we have two carbon atoms, we call it ethane. Methoxyethane. If it's three, methoxypropane. If it's ethyl, that is ethoxyethane. If it's propyl, that is propoxyethane. Do you understand? If it's propyl, that is propyl propanoids. You understand? So that's basically it for that. Should I talk about isomerism, but I don't think that girls will do that now. But let's just see. So I talk about isomerism because they used to ask. I'm just thinking about the things they can ask you randomly. Alright. If this is pentane, so if this is pentane and you are asked how many isomers does pentane have, simple. They are trying to ask you how many ways can you rearrange this compound to still maintain C5H12. C5H12. How many ways can you rearrange this to still maintain C5H? This is a popular question. So the first one is to break the bond. Like since it's 5 straight chain, cut it to 4 straight chain. Add the last chain here. Don't add if you add the last chain where you cut it from, that means there is no point of cutting because you cut it from this particular carbon. This carbon is attached to this particular carbon. So if you cut it and then add it here again, it doesn't change anything because it's that same carbon that you attach it, so it still retain the original name. So you cut this carbon and then put it either here or here, but not on the same carbon you moved, so, and not here, because if you put it here, it will retain the original name. Right? Not so, don't put at the end, put at the middle. You understand? So if you put at the middle here, you're going to have hydrogen every other places. Then you have another carbon here, and then hydrogen. This is the first isomer. The second isomer, you can decide to this first isomer is known. This is normal pentane. This is normal pentane. If you decide to put this here, it will also be 2-methyl-butane. It will also be 2-methyl-butane, right? So now, that means you have to cut again. If you cut again, you have 3. The remaining 2 carbon, put 1 here, put 1 here. Okay, let me do this very well. So, first of all, we have to cut into 1, 2, 3, 4 from 5, and we did this. There is no other place we can place it. If we place this in here, it will still be 2-methyl-butane. We should do this. So we have to cut it again to 3. 1, 2, 3. Then the remaining 2, we place it here and here. So still retain 5. Then H12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right. So if you name, this is 1, 2, 3. We have this and this all on carbon 2. So that's 2, 2, di. They are the same thing. They are methyl group, and they are the same thing. So dimethyl propane. That means pentane has what? 3 isomers. Take note of that. We also include the normal pentane as part of the isomers. Don't forget. Don't go and say it's only 2. There is no other way we can rearrange this thing to still get a different name. So pentane has 1, 2, 3 isomers. It's a popular jam question. How many isomers are there in pentane? If you see, just pick 3 and be going your way sharp. There's no time. Right? Now, guys, notice that there are 2 methyl groups. So that's why I say 2, 2 dimethyl propane. We use comma to separate numbers, and we use hyphen to separate numbers from letters. Numbers and letters, you see hyphen. Number and number, you see comma. Now, when you have a group of substituents in a compound that are not the same, you name them alphabetically. For instance, for instance, so this is 1, 2, 3, 4, 5. Or you can say 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Whichever way, you still have methyl on carbon 2 and ethyl on carbon 3. Right? If that is the case, what would be the name? We have methyl on carbon 2 and ethyl on carbon 3. You name alphabetically. E comes before M. So you have 3 ethyl, then hyphen 2 methyl, then longest chain 5 pentane. Right? 1, 2, 3, 4, 5. 5 carbon atoms. That's why I have pentane. The ethyl group that was not touched, which is a substituent, is on carbon 3. It starts with letter E, so it will come first before the one on carbon 2 that starts with letter M. So there are two different substituents, but they are not the same. So we name them alphabetically. But if they are the same, what will it be? It will just be 2,3 di. If it's ethyl and ethyl, it will be 2,3 diethyl. Blah 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 blah. If it's methyl and methyl, it will be 2,3 dimethyl pentane. Do you understand? So that's it about naming. You can explore and always ask questions whenever you encounter a problem you cannot solve. And from look of some of you have gone off already, and yeah, I believe you've quite refreshed your memory on chemistry. I forgot something very important in gas laws. I just remembered. Partial pressure is equal to partial pressure of a gas is equal to mole fraction times total pressure. This is under gas laws. I only did Boyce and Charles law. Pressure law. Pressure is directly proportional to temperature. This is also known as Gay-Lussac's law. Though we still have Gay-Lussac's law of combining volume and all of that, but this formula is important. Where when you are asked to find the partial pressure of a particular gas amidst others. So let's say they gave you oxygen, nitrogen oxide. These are gases. Okay. And let's say you have a group of gases, and they tell you that the total pressure, that's P total, is the total pressure. This is partial pressure. This is mole fraction. So let's say the total pressure is equal to 580. And you are asked to calculate the partial pressure of nitrogen 4 oxide. So what do? It's simple. Partial pressure of nitrogen 4 oxide will be equal to mole fraction of nitrogen 4 oxide. Mole fraction is the required mole divided by the total number of moles. The mole of what is required is NO2, 0.1, divided by the total number of moles, 0.1 plus 0.3 plus 0.4 times total pressure, 580. Right. So when you multiply it, you get the partial pressure of nitrogen. This is a very important aspect of gas laws that I forgot. Right, so please commit it into memory as well. Right, would have loved to go further, but unfortunately, things have to be this. I think I've covered quite a lot of topics that you need to know, just those important things that you need to know. We've touched stoichiometry in our first video, and we recapped stoichiometry, separation techniques, gas laws, acid, base, and salts, periodic table, periodicity. Let me take it again. We started with separation techniques. We moved to periodic table, chemical combination. We did formula of compounds. We did acid, base, and salt 5. We did gas law 6, did stoichiometry, a touch of stoichiometry 7, a touch of electrolysis 8, a touch of organic chemistry 9. Right, so I kind of brushed through like the most important aspects of it. All right, so to avoid boring you, the most important thing is make sure that everything that we did, you go through them, especially all these important points I'm saying. Take note of them, and subsequently, if there is time, we're supposed to do for physics, and I'm supposed to do an oral English class for you guys if there is time before your exam. All right, and I pray we'll have a time for that. All right, so thank you very much for staying tuned. Those of you that share to your friends, thank you very much. I really appreciate it. This is just what we do, the little we can do to help students excel. I hope to see you excel academically. All right, the group chat was supposed to be unlocked, but unfortunately, today of all days, there was no light in school, right? And it was frustrating, but we'll try to keep the group active so you can ask your questions at your convenience, time and you get responses. All right, so bye for now. If you have questions, you can either ask in my DM on WhatsApp. If you don't have my WhatsApp number, you can get it on the YouTube channel. I think it's there. Yeah, you can get it there. Or if you do, you can ask your questions on WhatsApp or ask it on the group chat. If you don't have if you're not in the group chat, you can send it to you when you send me a message on WhatsApp. Right, it's just free for all aspirants, so that you can get in touch with other aspirants and familiarize yourself with the questions before the exam day. Right, thank you, and do have a good night rest. When you sleep tonight, wake up tomorrow morning, go through all what you have done, go through your past questions, try to answer past questions based on what you have done so far. And I know we might, like I said earlier, we might not do everything. That is not even possible to exhaust the whole level, but that's why it's called revision. We are simply touching the important aspects. And I want to encourage you not to give up. You see, last minute preparation, it can change a lot. 2-3 days before your exam can be a game changer for you. I know some of you are thinking, can I still make it like this? Are you sure it's possible? Me that don't like physics, me that don't like chemistry. Everything is possible, right? With dedication, seriousness, determination, you succeed, right? And I wish you all the best in your exam. Before a day before the exam commences, you're going to do a prayer in the group chat to pray for each and every one of you and commit the journey into God's hands, right? And we'll believe that God's going to help you all do well and excel as well, right? So that's it. See you on our next revision class, which should be on Wednesday for physics, or most probably. All right, bye. Oh, you can leave the call now. You can leave the call or the live. All right, we'll try to keep it